well as Professor Tu. So let me continue. We had one CSTR or two CSTRs in series. Here we had G tilde of S, which is 1 over 1 plus ST. And here we have G tilde of S, which is 1 over 1 plus ST1, 1 over 1 plus ST2. And of course, I can have a KP here. And so G tilde of I omega is KP over 1 plus I omega t. And here, G tilde of I omega, in the case where T1 is equal to T2, is just Kp over 1 plus I omega t squared. And we started just going through, reviewing how I actually calculate this. So let's note that the magnitude of the amplitude ratio is the magnitude of G tilde of I omega. And that's the magnitude of Kp over 1 plus I omega t. And the way we get a magnitude is we multiply by 1 minus I omega t over 1 minus I omega. And the reason for that is because if this is the real and this is the imaginary axis, and this is a complex number, the real part is x, and the imaginary part is y. So if I want the magnitude of c, the magnitude of c is the square root of x squared plus y squared. So that's exactly what I'm doing here, is I need to write z as x plus iy. If I can write c as x plus iy, then I can calculate its magnitude as x squared, square root of x squared plus y squared, and phi I can calculate as the arctangent of y over x. So I need to have the I in the numerator, not the denominator. The way to get rid of I in the denominator is to multiply by the complex conjugate. Because if I multiply this out, I get the magnitude of Kp. And in the numerator I have, well, let's see the denominator first. The denominator, I'm taking 1 minus something times 1 plus something. 1 plus something times 1 minus something is 1 minus that thing squared. So 1 minus I omega t quantity squared, I squared is minus 1. So minus and minus is plus, and I have plus omega squared t squared. And in the numerator, so that's a positive quantity. In the numerator, I have the magnitude of 1 minus I omega t. So now I have the real and the imaginary part. X is just Kp over 1 plus omega squared plus omega squared t squared. And y is I minus omega t, Kp over 1 plus omega squared t squared. So the real part of G tilde of I omega is just Kp over 1 plus omega squared t squared. And the imaginary part of G tilde of I omega is just equal to minus omega t over 1 plus omega squared t squared. So if I take the magnitude, so this is x, and this is y, then the square root of x squared plus y squared is the square root, well, I can factor out the quantities that are in both. I also need Kp. So I have Kp divided by 1 plus omega squared t squared. And now I take the square root of this thing squared plus this thing squared. So I need the square root of 1 squared plus minus omega t squared. So I factored out the Kp, that's in both, and the 1 plus omega squared t squared. And what's left here is a 1, and what's left here is an omega t. So this is 1 plus omega squared t squared. So I get Kp times the square root of 1 plus omega squared t squared over 1 plus omega squared t squared. gives me Kp divided by the square root of 1 plus omega squared t squared. So I did that calculation last time. I just wanted to do it again so you would see how to do it. And moreover, I can find phi is the arctangent of y over x, is the arctangent of this guy over this guy. Well, this guy over this guy, the Kp and the 1 plus omega squared t squared cancel, and I just have minus omega t. So this is the amplitude ratio, and this is phi, the phase lag. And why don't we plot them before doing it for 2 CSTRs and series? So let's plot them. And the way we plot them is we plot the log of the amplitude ratio versus the log of omega, and also phi versus the log of omega. So let's look at that. The amplitude ratio, here we go, versus log omega. And we're going to do this for Kp is equal to 1. So I don't have to worry about the size of Kp. So notice that when omega is 0, so the log of omega goes from 0 to infinity. When omega is 0, the log of omega is minus infinity. The log of 0 is minus infinity. So when omega is 0, then I just have Kp, which we've assumed is equal to 1 over 1. So as omega goes to 0, the amplitude ratio goes to 1. So this is 1. And we know that it eventually goes there, but I have to go to minus infinity to get there because I'm plotting versus log of omega rather than omega. How about when I go to plus infinity? When I go to plus infinity, then omega, the denominator gets very big, and the whole thing becomes 0. So the amplitude ratio goes down to 0, and we know that it looks something like this. So this is a plot of log of ratio, the amplitude ratio versus log of omega. How about phi? Well, in order to get phi, I need to know the arctangent. So here is 0, pi over 2, minus pi over 2, minus pi, minus 3 pi over 2, plus pi, plus 3 pi over 2. And what does the arctangent look like? Let's use a different color chalk. The arctangent, when we showed last time, looks something like this. It goes to infinity when the cosine is 0 at pi over 2 and minus pi over 2, and it's 0 when the sine is 0. However, the cosine is not just 0 at pi over 2 and 3 pi over 2, minus pi over 2. It's 0 at all odd numbers of half pi's. So this actually repeats. So this is the arctangent of phi versus phi. So that's sort of what it looks like. All right, so let's now look at this expression right here. Here we have when omega is 0. When omega is 0, that means all the way to the left. When omega is 0, look at the arctangent of 0. The arctangent of 0 is 0. At least we're going to choose this value. So let's say this is 0. And we know that it's eventually going to go there. How about the when omega goes to infinity? When omega goes to infinity, it's the arctangent of minus infinity. The arctangent of minus infinity is minus pi over 2. So I know that for one CSTR, the Baudet plots look like this, and these are called Baudet plots. Any questions on that? On what a Baudet plot is and how to do it for first-order system? Okay, so now let's try to do it for a second-order system. 2 CSTR systems. Okay, so two CSTRs in series, we have, it looks like this. This is just the square of this. So the magnitude of the square is the square of the magnitude. We know that the magnitude of g squared is just the square of the magnitude of z. So you can easily verify that by, so this you can verify by homework. In other words, write out z as x plus iy, square it, and then take the magnitude. And then show that it's equal to first taking the magnitude and then squaring that. In which case, I know that the magnitude of g tilde of I omega for two CSTRs, if T1 is T2, is just equal to the square of this. So it's equal to Kp2, Kp for two CSTRs, divided by 1 plus omega squared, T squared, so the square root squared. Another way of seeing that, I could have just seen that, is if this were, what I would have is I would have this as Kp over 1 plus omega t, I omega t, times 1 plus I omega t in the denominator. So instead of multiplying by this once, I multiply by this twice. When I multiply by that twice, well actually I'm going to need to do that for 5, so I might as well do it. So let's notice that g tilde of I omega, in this case, with two CSTRs in series, is Kp over 1 plus I omega t, 1 plus I omega t. And I need to multiply that by 1 minus I omega t, 1 minus I omega t, 1 minus I omega t, 1 minus I omega. Because this one gets rid of the I, this gets rid of the I from here, and this gets rid of the I from here, and then I only have I's in the numerator. So let's see what I get here. So first, Kp, in the denominator, I have this product, I know what that is. It's just equal to 1 plus omega squared t squared. This product. And I have that product twice, so I have 1 plus omega squared t squared squared. Because I have one of those products from here, and then I have the same thing again. But now I have 1 minus I omega t quantity squared. So why don't we take that? So if I take this, I have 1 times 1 is 1. I omega t times I omega t with minus squared minus omega squared t squared. Minus I times 2 omega t. So there I have g tilde. So all I did was I took the original value and I got rid of the i's in the denominator. And now what I'm going to do is I'm going to verify that this is in fact the case. So let's verify that. So to get the magnitude of g tilde of I omega, I have to take the square root of x squared plus y squared. I factor this out, because that's in both. And I take the square root of this squared plus this squared. So let's see what that is. This squared is 1 plus omega 4 t4 minus 2 omega squared t squared. I squared that. And now I have to square minus 2 omega t. So minus squared is plus 4 omega squared t squared. Well, minus 2 plus 4 is just plus 2. And this whole thing just becomes, so this just becomes Kp2, 1 plus 2 omega squared t squared plus 4 omega 4 t4. It's just 1 plus omega squared t squared squared, and I take the square root of that, divided by 1 plus omega squared t squared squared. So inside the square root, I just have 1 plus omega squared t squared squared. So the square root and square cancel, and I just get one of them in the numerator and 2 in the denominator. So this just gives me Kp2 over 1 plus omega squared t squared. Exactly what we said. I'm sorry? That's an I, yeah. And let's calculate, so that's the phi. Phi is the arctangent of the imaginary part over the real part. Well, since the imaginary part has this factor and the real part has that factor, they both cancel. So it's the arctangent of minus 2 omega t over 1 minus omega squared t squared. So that's the amplitude ratio. And now let's make the Bouguer plots. So I've got the log of the amplitude ratio versus the log of omega. And let's see what that looks like. Well, again, this is for Kp2 equal to 1. So I don't have to, otherwise I just multiply the y-axis by Kp2. Well, what happens when omega 0? When omega 0, I just get 1 in the denominator and 1 in the numerator. So again, it looks like this. But what happens when omega gets large? And actually, I think I did this wrong, so I want to fix this as well. First, let's fix this. Let's do this right, and then I'll fix that. Okay, so what happens when omega, yeah. So let's look what happens when omega goes to infinity. When omega gets very large, then I can drop the 1. And the log of this, so let's look as omega goes to infinity. Then the log of the amplitude ratio is equal to the log of Kp2, which we said that we're just going to ignore that. We said that this equal to 1, so this is 0, minus the log of 1 plus omega squared t squared. Well, when omega is very large, I can neglect the 1. So this becomes minus the log of omega squared t squared, which just becomes minus 2 log omega t. So that tells me that this, if I'm plotting versus the log of omega, so this is equal to minus 2 log omega minus 2 log t. So that says that I should get a slope, a curve with, if I'm plotting versus log omega, I should get a straight line of slope minus 2. So this will eventually give me a straight line where the slope is minus 2. And I need to fix this because when I did this is not correct, what I wrote here. So let's do it for one CSTR. The log of the amplitude ratio is equal to the log of Kp, which again, we're assuming is 1, so this is 0, minus 1/2 the log. 1 plus omega squared t squared. Because I have the same denominator but with the square root here. So when I go through the same calculation as omega goes to infinity, instead of this just being minus log, it's minus 1/2 log. So I should just get minus 1/2 of 2 log omega plus log t, plus 2 log t. So the 2's cancel. And when I plot, I should get something that goes as a linear function of log omega with slope minus 1. So this one should look similar, except it has slope minus 1. Whereas for 2 CSTRs, it has slope minus 2. This decays much faster. So I think last time I had done this incorrectly. So now this is correct with the slope minus 1, and here the slope is minus 2. Any questions on that? So now let's look at phi. Phi is a little bit more tricky here. We said phi is the arctangent for 2 CSTRs. Here it is. So so let's look at what happens to phi when omega is 0. Then the arctangent 0 is 0. So as omega goes to 0, phi goes to 0. So that part is fine. And this is log omega. happens as omega goes to infinity? As omega goes to infinity, I can eventually drop the 1 because this becomes much bigger than 1. And then what I'm left with, the minuses cancel, 1 omega t cancels, and this thing goes to 2 over omega t. Over omega t. Okay, so what happens there? So this is equal to 2 over e to the log omega t. Let me write it that way. Okay, so what happens as omega goes to infinity? When omega goes to infinity, phi goes to, looks like it should go to the arctangent. I don't really need this now. So it looks like this should be the arctangent and go to the arctangent of 0. But the arctangent of 0 would say it goes back up to 0. We will see later, now the arctangent of 0 is ambiguous. The arctangent of 0 could be 0, it could be pi, it could be minus pi, it could be minus 2 pi, etc. So there's an ambiguity there. And right now, it's not clear why we choose what I'm going to choose. In about a week or two, it will become clear. But just for completeness, it turns out as omega goes to infinity, I end up choosing minus pi. And the way I would know that is by actually doing this calculation, not just for omegas equal to 0 and omegas equal to infinity, but doing it for the omegas in between. And how do I know that? How do I know I'm going to get to minus pi? Because let's say I pick an omega that's finite, that's not 0 and not infinity. Let's say it's a small number. So if it's a small number, so omega t is less than 1, then the numerator is negative, the denominator is positive. If the numerator is negative and the denominator is positive, then remember I came from 0, then the arctangent of a negative number is negative. So if I keep on following, the arctangent of a negative number is negative. When I get to minus pi over 2 goes to minus infinity, but eventually it becomes positive again. So that's not really a very convincing, so it becomes positive again, because when omega squared t squared equals 1, then this thing becomes infinite. So I'm on minus pi over 2. But as soon as omega squared t squared exceeds 1, then the denominator is negative, the numerator is negative, the ratio is positive, and for omega t very close to 1, it's infinity. So I'm switching from this branch to this branch. I'm going from minus infinity to plus infinity. And then when I follow it further down from omega goes to infinity, that is, where the denominator dominates the numerator, I move down this branch to minus pi. So I'm not sure that's so easy to follow, and we'll have an easier way of doing it in a week or two. But that's why this thing goes effectively like that. So as omega goes to 0, it goes to 0. As omega goes to infinity, it goes to minus pi. How are we doing? Are there any questions on that? Yes? Can you speak a little louder, please? I'm sorry. Why I chose the minus pi. Again, it's going to be a lot clearer. There's a better way of doing it in the future. But just a quick rundown. If we start, so sometimes you just look at the limiting values, 0 to infinity. What I'm doing here is the way to know which value to use for infinity. I start at 0 when I increase omega slowly. And I look to see the continuum of how I get there. So when omega is 0, I have the arctangent of 0. Because it's 0 over 1. So clearly, I just get 0. So that's here. Now if I start increasing omega t from 0, it's not 0, but it's a small quantity. When it's less than 1, then the denominator is positive, the numerator is negative. So when I go from here, I have the arctangent of a negative number. As omega goes up, I'm moving to the left on here. Eventually, when omega t gets to 1, just before it gets to 1, this is still positive, but it's getting close to 0, and this thing is negative. So the ratio goes to negative infinity. So I'm following it down to here when omega t is 1. As soon as omega t gets a tiny, tiny bit bigger than 1, this is still close to 0, but it's positive. I'm sorry. It's still close to 0, but now it's negative. So if it's negative, then the ratio, instead of being minus infinity, jumps to plus infinity. So I've jumped from minus infinity to plus infinity. And now when I continue following it, as omega gets bigger, well, this thing becomes more and more negative. So the denominator becomes bigger but negative. So the magnitude goes down. This is a square. It goes down. And eventually, when omega gets to be infinity, so that the ratio is 0, I move down this curve to here. So I'm following it just by continuity, is how I know that I should be here and not here. Is that clear? Now, I don't expect you to go through that argument all the time. There'll be another way of doing it where it's clearer. And that's going to be using a little bit of complex variables. Okay, one more. Let's look at a plug flow. In a plug flow reactor, we show that G tilde, that's just a plug flow, says that Y prime is just if there's no reaction. Then Y prime is of T is just X prime of T minus tau. It's just a delay. What's coming out is just what came in, but tau seconds later. What came in tau seconds ago. Do I have that right? So when t is tau, yeah. Okay, so y prime tilde is equal to x prime of t minus tau. Well, so y prime tilde is just a delay, is e to the, it's either plus or minus x tau x prime. I think it's minus. Check, I don't recall. For delay, yeah, it's minus. So g tilde of s is y prime tilde over x prime tilde is just equal to e to the minus s tau for a plug flow reactor with no reaction. Now, a plug flow reactor with no reaction is not very exciting, but we're starting with the unexciting things. We'll get to more exciting stuff later. So now let's calculate the amplitude ratio. The amplitude ratio is the magnitude of g tilde of I omega, which is the magnitude of e to the minus I omega tau. But we know that e to the minus I omega tau is cosine omega tau, cosine minus omega tau, plus I sine minus omega tau. But the cosine of minus is the same as, this is just the same thing as cosine of omega tau, because the cosine is an even function. And the sine is an odd function. And the magnitude is just the square root of sine squared omega tau plus cosine squared omega tau. And what's sine squared plus cosine squared equal to? 1. So this is just 1. The amplitude ratio is just 1. And how about so the amplitude ratio is 1. And how about the phase lag? Phi is the arctangent of the imaginary part of this over the real part. The imaginary part is sine of minus omega tau over the real part is cosine of minus omega tau. So it's the arctangent of the tangent of minus omega tau, which is just minus omega tau. And let's do the Baudet plots for this. So if I do the log of the amplitude ratio versus the log of omega, well, the amplitude ratio is always equal to 1. What's the log of 1? 0. So it's just this. Boring. I said it would be boring. There's no reaction. So it's boring. Unlike the rest of this class. Let's look at phi. So if I want to plot phi versus log omega, I need to rewrite this. I want to get it in terms of log omega. So this is equal to minus tau e to the log omega. Because my variable is log omega, not omega, in this plot. So this says that phi looks like an exponential function, because this is my abscissa, but with a negative sign. So instead of looking like this, it's upside down, and it looks like this. So it looks like an upside down exponential multiplied by tau. So there I have that. Are there any questions on that? Now, you might ask, and it's legitimate to ask, why am I making these plots? Am I just making these plots to eat up time or to bust your chops? Any of those are possible. Of course, I wouldn't bust your chops. As we'll see later, it's very often helpful. You can do certain calculations just with the graphs. We'll see later on. And sometimes it's easier to do the calculations with the graphs than it is algebraically. So we're getting used to making these plots because later on we'll use them. In chapter 10, we'll use them. Any questions on that? Okay, so questions? We lost like half this class to room businesses, but we'll do the best we can. Okay, so what I'm going to do now, it's in chapter 5, is to sort of formalize some of the algebra we did before, put it in sort of a standard form. So if we look at what we call first order systems, which is essentially what we did here. It's essentially what we did here. But I want to put it in a standard notation. So the standard notation we put it in is t, so y is going to be the output, dy dt plus y is equal to kpx, right? Yeah, kpx. And I'm going to leave out the primes. I'm going to assume that these are already prime variables. So this is just a standard form where t is the time constant, y is the output, and x is the input. So the algebra is what we've done before. We can Laplace transform. If we Laplace transform, we get sy, and here we tilde and y tilde. So 1 plus st y tilde is equal to kp x tilde. Well, y tilde over x tilde is equal to kp over 1 plus st. Exactly what we had here. No big surprise. Just here I've just written it in a standard form. And let's just, to be explicit, let's look at what happens. Let's look when x, if x is a set, and if x is a pulse. So if it's a step, then, so these should all be primes, but I'm not going to worry about that. Then x tilde is equal to delta x over s. And if x is a pulse, then x tilde is just the size of that pulse, say n. It's the amount in the pulse. So in that case, y tilde is kp delta x over s1 plus st. Here, y tilde is equal to kp m over 1 plus st. And when I invert, we're going to get kp delta x. So I times the inversion of the 1 over s, 1 over 1 plus st. We've done this before, so I'm a little rushing through it, which is line 5. Line 5 in the table, I get 1 minus e to the minus t over t. We've done that before. And if I don't have the 1 over s, then it's line 4, and I just get kpm times 1 over t e to the minus t over t. Or again, as we've said earlier, this goes back to a new steady state at infinite time. It goes to kp delta x. And this goes back to where we started. That is, it forgets the pulse, but it doesn't forget the step, because the step continues forever, and the pulse was only t equals 0. And similarly, anything else I want to say about that? And similarly, we know that g tilde by omega, we've just done that, is kp over the square root of 1 plus omega squared b squared. And phi is equal to the arctangent of, I just did it, minus omega t. So that's all just a repeat of what we did before, but in this notation that we want to call generic notation. Are there any questions on that, since that's all a repeat or rerun? So this was the summer programs on TV. Now we're going to go to the fall program. Now let's look at a second order system. So in this case, I have T1, and I know I'm going to have to close these, so I'm not going to do that. Oh, now look for the teacher. Okay, second order system. T1 dy1 dt plus y1 is equal to kpx and kp1x, and t2 dy2 dt plus y2 is equal to kp2 y1. So you can think of this as two CSTRs in series. X is the input to the first CSTR, and what comes out of the first CSTR is y1, and that goes into the second CSTR. Here, without rewriting it, all variables and y's are prime. I'm just not going to keep writing the primes, just a mess. Okay, so what I'd like to do, rather than solving this the usual way, I want to put it in a slightly different form. Let's notice that I can solve for y1 from here. If I solve for y1, I have that y1 is equal to t2 over kp2 dy2 dt plus y2 over kp2. And then I can plug into here. I plug into this expression. So wherever I see y1, I'm going to plug that. So I have t1, t2 over kp2, d dt of this, d squared y2 dt squared, plus t1 over kp2 dy2 dt. So what I did is I took the expression for y1 and I plugged it in right here. Now I'm going to add a y1. So now I have plus t2 over kp2 dy2 dt plus y2 over kp2 is equal to kp1x. And notice this is of a particular form, and I can write, I'm going to multiply through by kp2. And notice I have t1 t2 times d squared y2 dt squared plus t1 plus t2 dy2 dt plus y2 is equal to kp1, kp2, x. So this is an equation for a second order system. So here I've combined it before solving. And notice a second order system. In the first order system, the highest derivative I had was the first derivative. And therefore I only got one power of s in the denominator, because that came from the first derivative that gave me an s. When I have a second order system, I can manipulate it so that you see there's an obvious second derivative. The second derivative is going to give me an s squared in the denominator. And we know we get an s squared in the denominator because we know that in general what it looks like when I solve for g2, I get 1 plus st1, 1 plus st2. Now, this is of course two CSTRs in series. What I'd like to do is I'd like to come up with a more general second order system. Where I'm going to call it t squared, e squared y, dt squared, plus 2tc, dy dt, plus y is equal to, what do I want to call it? K plus 2ct, what is equal to kp x. So here I'm generalizing this a bit. How am I generalizing? Here I'm allowing c to be anything I want, any number. Whereas here, there's a relationship between the coefficient of the first derivative and the second derivative. Here, in this case, it's more general because I'm letting c be anything I want. And c is called the damping coefficient. Why is it called the damping coefficient? Well, from freshman physics, when you look at the problem, say, of a pendulum, simple harmonic motion, you've got force is equal to the mass times the acceleration. The acceleration is a second derivative with respect to time. And the force is, say, a spring force, or let's say it's a spring force. It's minus kx. So here I have the second derivative from the mass times the acceleration, the mass times the acceleration. And if this were on the other side of the equation, I would have a minus ky, where y is the displacement. If you recall from freshman physics, if you include friction in that case, then I also have a negative force opposing the motion, minus a friction coefficient times the displacement, or times the velocity. So the velocity is the first derivative. So recall, if I have a block on a string, a mass, and this is the displacement from equilibrium is called y. So then I have the mass times acceleration, the mass times d squared y dt squared. Mass times acceleration is equal to the sum of the forces. One force is minus ky. That's the spring force. And then I also have minus b times dy dt. And I'm going to call it c here. And this is the frictional force. So if I just move these to the other side of the equation, I can see that e squared y squared and t squared represents the acceleration in this problem. This term represents the spring force, and this term represents the damping force. And that's why we call C the damping coefficient, because it represents, let's just do the D, because it represents the frictional force. In this particular example, it represents the frictional force. Questions? Is that clear? That's the motivation for doing this. So notice you can get second order systems not just in control, but in many situations. So now let's do the, and of course, I can always, this is a special case of this. For a particular value of t and a particular value of c, I can get this. So for example, say for special case 1, we would have t squared is t1 plus t2, and 2ct would equal to t1, t2 plus t2. Let's see. This is t1 times t2, and this is t1 plus t2. So I can easily solve for that. I know that t is the square root of t1, t2. And c is equal to t1 plus t2 over 2 square roots of t1, t2. So for this special case, I can identify t as the square root of t1, t2, and c as t1 plus t2 over 2 square roots of t1, t2. Well, let's solve this equation. Let's do Laplace transform. If I have a Laplace transform, I get t1, t2. This now gives me an s squared, because these are all prime variables. So I don't have to worry about initial conditions. So I've got s squared times y2 tilde. I've got y2 tilde times t squared. I'm looking here. T squared s squared. And now I have plus, this gives me an s, 2tcs plus 1 times y2 tilde is kp x tilde. By the way, in this particular example that I did here, I identified the physical meaning of all three of these terms. I didn't identify the physical meaning of this. This is an external force that's pushing. I can, in addition to allowing the mass to just go back and forth under the spring and force and the frictional force, I could also push it. So this is the pushing force. Which is an external driving force. Okay, so now I just did this, and I have that y2 tilde over x tilde, which is g tilde of x, is equal to kp over 1 plus 2 tcs plus t squared s. And what I want to do is I want to look at the roots of the denominator. First, to look at stability. To look at stability, I need the zeros of the denominator. So that's equal to s roots are equal to, okay, so it's minus b 2tc plus or minus the square root of b squared 2tc squared minus 4 times 1 times b squared over 2a, 2t squared. So let's simplify that. So this is equal to, I can in fact take 1t from here and kill out these and these. Factor that. I also can factor the 2. The 2 kills the 2 here, kills the 2 here, and kills that. So this gives me minus c plus or minus the square root of c squared minus 1 over 2. So let's notice what I'm left with. Remember, if I'm interested in stability, I need to know these roots. So the first thing I can see, if I make this move here, is c squared. Then I have very different behavior for c greater than 1 and c less than 1. So, first case, c greater than 1. If c is greater than 1, then the square root is, then the thing inside the square root is real, is positive. So the square root is real. Moreover, the square root of c squared minus 1 is less than the square root of c squared. So the magnitude of this thing is smaller than the magnitude of c. So even when I add this quantity to the minus c, it has a smaller magnitude than c. So the whole thing is still negative. So both roots are negative. Both roots are negative, and therefore it's stable. Both roots are real and negative. Real and, right, negative. So it's stable, and it's overdamped, meaning there's no oscillations. Overdamped. On the other hand, case B. Well, C is equal to 1. If C is equal to 1, then this is 0, and I just have double root, a double root. And if I have a double root, that's what we call resonance. And when we solved, we found that the solution, y, goes like t e to the minus t over t. So, whereas this decays exponentially, this initially rises and then decays. So it rises and falls. It's not monotonic. But I can say that because it's small with t, the exponential is close to 1, and it just rises with t, and eventually, as t gets bigger, the exponential wins, and it goes down. Something like that. And case C. In case C, C is less than 1. What happens when C is less than 1? When C is less than 1, then C squared is smaller than 1. And this becomes a negative quantity inside the square root of the discriminant. And the square root of that is imaginary, so this becomes complex. Complex conjugates. But they have negative real parts, both with negative real parts. So if I have complex conjugates with negative real parts, then remember I get oscillations because I get sines and cosines times an exponential. So I get something that looks like e to the minus t over t times sine omega t plus cosine omega. In other words, it oscillates and decays. It's underdamped. Are there any questions on that? Now, let's notice that one thing to notice is that in a first order system, notice that the amplitude ratio, this is the amplitude ratio, for any value of omega, the amplitude ratio is less than kb. So if you like, if kb were 1, this thing becomes smaller because the denominator is bigger than 1. On the other hand, here, in a second order system, the amplitude ratio, which is the magnitude of kb over 1 plus 2tc I omega plus t squared times I omega squared. I squared is minus 1. So I need to figure out what that is. That's equal to, so to do that, I multiply by 1 minus t squared omega squared minus 2tc omega I over 1 minus t squared omega squared minus 2tc omega I. So here I have 1 minus t omega squared t squared minus I times 2t c, 2 omega t c. And in the denominator, I get 1 plus 1 minus t squared omega squared squared. Plus 2tc omega 1t squared. Now, how did I get that? I got that because I have the real part minus the imaginary part, and here I have the real part plus the imaginary part. So when I have a minus b times a plus b, I get a squared minus b squared. So that's the real part squared, and the imaginary b is I times this quantity. Minus I squared is plus, and here is the rest of it squared. And here I have the real part and the imaginary part. Now I need to take the magnitude. And in the numerator, I have 1 minus omega squared t squared squared. And now I need to take plus this thing squared, plus 2 omega t c squared, square root. So, just make sure I do that right. The square root of that squared plus that squared, yeah. So this just gives me kp divided by the square root of 1 minus omega squared t squared plus 2 omega t c squared. So this is the amplitude ratio. And now we can examine this for a second and compare it with the amplitude ratio we had for a first order system. For the first order system, the denominator was always bigger than 1. So it always knew the amplitude ratio was always smaller than kp. However, over here, that need not be the case. For some values of c, since I have a minus here, and then I add something, if I don't add enough, this thing can still be less than 1. If I add a lot, this thing will be greater than 1. So when c is large, then the amplitude ratio gets reduced. But when c is small, in this particular case, then in fact it doesn't have to get reduced. The denominator can be less than 1. Okay, there was a lot of algebra there, but only a moderate amount of physics there. Are there any questions on that? Okay, because we've lost out some time based on the rooms, I'm not going to be able to do the rest of what I had planned on doing, which is about another 20 minutes worth of stuff. So let's just review what we've done today before we end the class. And unfortunately, we lost about 20 minutes, maybe even a little more, about a half hour running up and down and writing stuff. Okay, so what did we do today? We started out by reviewing what I did at the end of the last hour, which was to look at one CSTR, 2 CSTRs in series, and to illustrate. So during the last hour, we looked at the response of a system to a sinusoidal input. And we said that you can get all the important features of the sinusoidal response without inverting the Laplace transform. So we had an expression for the amplitude ratio and for the phase lag. So we actually illustrated it here for one CSTR and 2 CSTRs in series. We found the amplitude ratio and the phase lag for one CSTR in series, and the amplitude ratio and the phase lag for 2 CSTRs in series. And then what we did is we plotted them in the traditional way, which is called the Baudet plots, of the log of the amplitude ratio versus log omega, and phi versus log omega. And we saw there were nice limits here. This went down as with a linear slope 1. That's why we plotted against log omega, so we get a simple plot because the log of the amplitude ratio is linear in the log of omega here. Here we have a slope -2, and the Baudet plot looks a little different. Here, instead of going from 0 to -π/2, it goes from 0 to pi. That's a little hint of what's to come. We know that the two CSTRs in series multiplied things. It multiplied each of the CSTRs. And that's why the amplitude ratio, instead of having slope -1, had slope -2 in the limit, because it was like squaring it. Similarly, instead of squaring angles, angles add instead of being multiplied. So instead of having a reactor with a -π/2, we have the first one is a -π/2, the second is a -π/2. They added to give me a -π. We will see that formally in about 2 classes. We haven't seen that yet, but that's just a hint. Then when we, and for the plug flow reactor, we also calculated the amplitude ratio and the phase lag, and we then plotted them. It was a plug flow reactor with no reaction going on. Finally, we moved on to the formal, to essentially do the same thing, but in a little bit more unified notation. So for the first order system, it was exactly the same. I don't need to really belabor that. For the second order system, we had never bothered doing it in the past, but here we explicitly showed that you can take the equations for the two CSTRs in series, which is effectively what this is, and combine them to a second order equation, which sort of explicitly shows you why you're getting S squareds in the denominator. But instead of just dealing with that, we decided to generalize it a bit to allow for xc for a damping coefficient for more generalized second order system. Remember, in this situation, I don't have the freedom to set this coefficient for what I like. It's related to this coefficient. Here I can choose any xc I like. So when you do that, allow xc to be anything you want, your Laplace transform, we found that we could get, unlike here, where the roots were always -1/t1 and -1/t2. If you remember, the roots here were the zeros of the denominator were -1/t1, -1/t2. And this was always stable and overdamped. When I have xc here, xc can be, when xc is large, that's effectively what happens. But when xc is small, and this would be the case with t1 equals to t2 in the upper one. But here, we also allow xc to be small. When xc is small, then we can get oscillatory behavior. We can get a system that's underdamped. And now we just calculated the amplitude ratio. And of course, phi, I should write it down, is the arctangent of 2 omega tc squared over 1 minus omega squared t squared. So we will start from these next time. We've calculated for the general second order system. But we already noted that when xc is arbitrary, then we no longer have a situation where the amplitude ratio is always less than kq. I know there's a lot of algebra, but we're going to be using all this for control. Are there any questions?